The first speaker is Samy who's going to talk about catalysis, supported on graphene oxide and other things, with the goal of making carbon-carbon bonds. So Samy, please, it's all yours.
Well, thank you, Mike. Thank you, everybody, and good morning. So it's really a great pleasure to be here for 15 years now. This is my 15 years here. Of course, I ran this meeting the first 4 years, and it's greatly impressive. That's still going on very strong. So thanks to Tony and all the IWAM team. So today, what I'd like to do is to talk to you about heterogeneous catalysis that's responsible for forming carbon-carbon bonds, which is extremely important, as you will see, in many applications, especially in pharmaceutical industry. So first, I want to give the outline of my talk. So I'm going to give a background about carbon-carbon bond formation. Then I will speak about developing palladium catalyst on graphene-based materials. That includes graphene oxide, reduced graphene oxide, chemically modified graphene oxide, and then graphene acid, which is kind of relatively new material that can be used also as a support for palladium nanoparticle catalyst. Then in the second part, I will talk about applying palladium catalyst to MUFs and bimetallic MUFs as supporting materials and discuss what kind of issues involved in that. And the last part is palladium catalyst also on carbonaceous oxide support derived from MUFs. So carbon-carbon bond forming reactions, there are several types of forming carbon-carbon bond forming reactions, usually known as cross-coupling reactions. Example of this, like if the coupling between two aromatic or two ring systems is done through a single bond, that's called Suzuki catalyst, Suzuki coupling. And you can see example of bromobenzene and boronic acid forming biphenyl. If the coupling is through a double bond, that's known as Hick reaction, and you can see bromobenzene with the styrene. And if the coupling is through a triple bond, that's Sonogashira reaction, which is phenylacetylene here with iodobenzene, and sometimes also can be chlorobenzene. So what's the big deal about these reactions? These reactions are extremely important in the formation of active pharmaceutical ingredients. So actually, drugs are made in one step from these kinds of reactions. There are many examples of actual active pharmaceutical ingredients, such as you can see some examples here. Rheumatoid arthritis, that's made by Merck. Asthma, that's made by Novartis. And anxiety drugs made by Merck again. Obesity drug. And you can see the coupling. This is the red bond that's forming coupling or connecting the two carbon bond, the two carbon centers. And here is HIV by Bristol-Myers, and from BI, also HIV, active pharmaceutical ingredient, which they all share one common thing, that they are made by palladium cross-coupling reactions through the systems that I described here. So these reactions are typically made or performed under homogeneous conditions, where the catalyst, of course, and the reactants are in the same phase, and they involve ligands. So you have metal ions ligated by metals, and they have very high activity. Homogeneous catalysis, they always have very high activity, but there are some problems with homogeneous catalysis. One is always residual toxic palladium compounds can cause a very serious problem. And there must be a lot of work and efforts to ensure the removal of any small residual palladium compounds in the products, which is the drugs that we talked about. The other important issue, which is kind of economical issue, they are very difficult to recycle. So the catalyst works one time, and is very difficult to separate and to recycle, so it requires a lot of expenses involving the catalyst itself and the ligands that's involved in that. So the goal of this area is usually to develop heterogeneous catalysts that's supported on some kind of support that will have very high activity and at the same time will not have leaching or sintering of the particles, so the catalyst can be recycled over and over, so that can provide economical advantage. Typically in heterogeneous catalysis, there are different types of support materials. One is the carbon-carbon support and the metal oxide support. This is the common support materials. They have very different characteristic features. The oxide supports usually they characterized by good activity, but some metal leaching from the oxide support. The carbon-based support is the opposite. They have typically low activity, but they also have less active or less leaching from the support. So the goal, and this is actually what we became interested in, is how we develop heterogeneous catalyst system that can actually exceeds the activity, surpass the activity of homogeneous catalyst. And in other words, what we want to do is increase activity of palladium on carbon-based support and decrease the leaching from palladium on oxide type support. So I'm going to go through the early work that we did here and then continue with what we just developed recently and what we continue to do at the time. So our first work here was based on palladium nanoparticle catalyst supported on carbon-based material, which we chose at that time to be reduced graphene oxide. And reduced graphene oxide can be also partially reduced graphene oxide, which basically is a graphene sheets, but containing several oxygen function groups, such as OH, epoxy, and a little bit of carboxylic groups. Why is that was a choice for a support that we expect to be providing active catalyst system? Because in this case, the reduced graphene oxide or the graphene type of support has a lot of defects because it's not a perfect sheet of graphene. It has vacancies. It has a lot of edges and grain boundaries, sp3 hybridization, and all these defects are signatures for developing actively catalyst, because the catalyst can be incorporated within these defects and can provide high activity for the reaction. So our first way to do this, we developed, of course, it's very easy, straightforward to make graphene oxide from hammer method, which is very well developed method from graphite. And the graphene oxide is characteristic by separate sheets that's well dispersed in water. Then we take this graphene oxide solution with a metal ion, the palladium salt, and we undergo two types of process. Either laser irradiation, which does not involve any reducing agent to reduce the palladium ion into palladium. I'm talking about palladium, but this is, of course, cannot be any other metal ions like I'm showing here, silver, gold, and many others here. So one approach is to use laser irradiation for the reduction of the metal ions. The other approach is to use a chemical reducing agent under microwave reaction conditions. In both cases, you end up forming nanoparticle catalyst supported on the reduced graphene oxide, because you have two types of reduction reduction of graphene oxide and reduction of the metal ions that you're interested in, which happen to be palladium in this case. As a matter of fact, we actually have two kinds of patents. One that reads, production of graphene and nanoparticle catalyst supported on graphene using microwave radiation. And the second catalyst is very similar title, except that using laser irradiation. Or laser radiation in solution. So this is the two process that usually we utilize to make nanoparticle catalyst, in this case palladium catalyst, supported on graphene or reduced graphene oxide in this case. Our first reaction was done in a long time ago, 2011, and that's the Suzuki coupling between bromobenzene and boronic acid. And you can see the conversion curves here. This catalyst was very active. You can see within like less than 20, 30 minutes, 100% conversion at room temperature. At the same time, the same concentration of the palladium nanoparticles, but on carbon black, it takes hours and it will never reach even like 40 or 50%. So the question was at the time, you have palladium nanoparticles in both cases. You have carbon-based support in both cases. Why is when the catalyst is supported on graphene-based material or reduced graphene oxide shows this very high activity? Actually, we measured turnover frequency with 108,000 products per hour at 80 degrees centigrade, and that was one of the highest value that's measured ever from a heterogeneous catalyst at the same time at that time of the reaction. We followed this by using the other methods to make the palladium catalyst by using laser irradiation, and in this case, the laser irradiation reducing the metal ions in solution actually produces more defects. And it can remove carbons from the support, and it can create a lot of vacancies and even holes in the support. So as a result, we can see that the activity becomes much higher, and we can see here turnover frequency goes from 100,000 before, now it's 220,000. It's a little higher temperature for this experiment, but still, even at room temperature, the activity was very high compared to the catalyst that made just by microwave radiation. So the laser radiation definitely produces a much more active catalyst, as we can see here. We followed this work by developing magnetic catalyst, which involves magnetite, which is Fe3O4. And we were able to optimize the percentage of magnetite on the reduced graphene oxide. And of course, the palladium is the catalyst here. And the best catalyst here, which about 6% palladium on magnetite reduced graphene oxide, with still converting the product within less than probably half an hour or less than an hour with 100% yields. And the advantage of this, of course, is that you have a magnetic material, so it's very easy to separate the catalyst. For recycling purpose, you can see this is the reaction product. If you just apply an external magnet, you can collect the catalyst easily and then separate it and use it for a different reaction. Following this, we tried to think how we actually modify the support, which is the reduced graphene oxide. So we had an idea, if we incorporate strong electron donors, two of them are mentioned here. One is paraphenylene diamine, and the other is benzidine. These are strong electron donors. If we chemically attach that to the reduced graphene oxide, we could have a scenario where we manipulate the electron donating properties of actually the support, which of course is very important in the cross-coupling reaction because the reaction goes from palladium 0 to palladium 2 plus and back to palladium 0. So it definitely involved electron transfer process, and is having a strong electron donor could be an advantage. It turned out that depending on the loading of this chemically modified materials, you can have two different kinds of arrangements. One where you have low loading, and in this case, the graphene sheets or reduced graphene oxide sheets, actually they are not very much separated from each other, they are closer. But if you increase the loading of the diamine or benzidine, you end up separating the layers much more, and in this case, you form much larger palladium particles. In the case where you are not separating the layers much, the particles are really small, and that's what we will see next. So you can, of course, get an idea about the spacing between the layers with the chemically modified graphene oxide here, looking at the XRD peaks and how they shift as a function of loading of the electron donor materials. So as I mentioned, with a small loading, we see that the separation is less. This is graphene oxide. The separation is 7.8 angstrom. If you put here 0.025 millimole of paraphenyldiamine, you see that the separation becomes less. It becomes 6.8 angstrom. But if you start increasing the loading, the diffraction peak starts to shift to the other side, and you can see increasing separation, which also is accompanied by increasing particle size, palladium particle size. We can reach here 1.2 nanometer, and with benzidine, you can see that we can reach 1.4 nanometer, and in both cases of this large separation, we have quite large palladium particles. This corresponds to this picture where we have a long separation between the layers and the formation of large particles as compared to a small separation, which involves very small palladium, relatively small, here like 2.2 nanometer with very small loading of the electron donor materials. The activity exactly is reflected in the particle size in this case, which is also mediated by the separation between the layers. So you can see with very small loading, 0.03 millimole, you have a very high active catalyst, and that corresponds to very small particles of palladium. As you increase the loading, you can see that the activity starts to go down, as he is showing here in the blue curve. And this is just the reduced graphene oxide by itself without any covalently bonded electron donor materials. The same result happens with benzidine. Low loading corresponds to higher activity. High loading the activity goes down. Very high loading, you can see the activity actually becomes very, very poor. And that corresponds to this picture, which very large palladium particles are formed. Therefore, there is not really much active sites in this catalyst system. So based on this study, using chemically modified reduced graphene oxide, we were able actually to use extremely small concentration of the catalyst. You can see the catalyst here is 0.007% mole of palladium. So this is a very, very small amount of concentration of palladium catalyst, and the reaction is still 100% complete in 2 minutes using microwave heating here at 80 degrees. From these results, we can evaluate the turnover frequency, and we find we went before from 100,000 to 200,000. Now, with adding the electron donors, we reach 400,000, 373 or 370. So the turnover frequency approaching 400,000 per hour, which quite close now, getting quite close to homogeneous catalysis in terms of this high activity. And the reason here is, again, manipulating the particle size and the electron donating properties of the support, which is the chemically modified graphene oxide. After that, this is the conclusion for the chemically modified reduced graphene oxide, that the partial functionalization of reduced graphene oxide can lead to strong activity. Examples here, paraphenylidene, diamine, and benzidine. And we can reach turnover frequency approaching 400,000, which close, very close to homogeneous catalysis systems. Following this, we were wondering what happens if we change totally the reduced graphene oxide and replace it with graphene acid. I'm showing here the difference. Graphene oxide has oxygen functional group, which is less overall than graphene acid. And the function group here are mostly OH, epoxy group, and some of the carbonyl group, and very little carboxylic groups. Graphene acid is characterized by having mostly a carboxylic group and overall higher concentration of functional groups than graphene oxide. The way to make graphene acid is to start actually from graphene cyanide. And you make graphene cyanide. This is a TEM picture of graphene cyanide flake. You make this actually from fluorinated graphite with potassium cyanide. Reflux over, you can form a graphene cyanide. And you can see clearly the CN band in the FTIR characteristic of the graphene cyanide. You take graphene cyanide and you do acid hydrolysis using nitric acid, for instance, at different times, at different concentrations. You can watch the disappearance of the cyano groups until you have complete disappearance at higher concentration and longer reaction times with the acid hydrolysis here. And you end up forming carboxylic groups, replacing the cyanide groups in graphene cyanide. You can see the XPS of the carbon 1s, and it shows a significant amount of the carboxylic groups here, in addition, of course, to the sp2, sp3, and carbon nitrogen and carbon oxygen groups. This is also TEM image of the materials showing EDS analysis, which shows the oxygen and carbon maps. The oxygen carbon is in red and the oxygen in green, which shows some kind of homogeneous distribution of the oxygen groups over the single flake that we're looking at here. So now we wanted to see if the activity of replacing the OH or increasing the carboxylic groups will have a significant effect on the catalysis with respect of graphene oxide with respect to graphene acid. So this is, we deposited the palladium nanoparticles, and this was done, in this case, actually, we did this by a hydrogen reduction of the palladium ions, and also in presence of copper ions. So we could form palladium copper bimetallic particles and palladium particle by themselves. This is on graphene oxide, the top two, and the bottom two on graphene acid. And you can very much similar size distribution particles, except of the palladium copper on graphene acid appears to be a little larger particles than on the graphene oxide. Then we look at the activities. to compare the bimetallic on graphene, which is the palladium copper, on graphene oxide and the graphene acid. We were actually surprised to see that graphene oxide is still a better support for both palladium copper, this is the palladium copper, and also for the palladium itself, which is this pink curve. So palladium on graphene oxide, palladium copper on graphene oxide, both of them behave higher activities than the corresponding catalyst on graphene acids. So it turns out that increasing the carboxylic groups did not enhance really the activity of the catalyst supported on graphene acid compared to the catalyst supported on graphene oxide. You should note that the reaction time here goes to minutes. Before we were showing several hundreds of minutes because the activity is much higher. Also, the catalyst concentration is much lower in this case than the examples I showed before. So to conclude this part, before also, we did also some theoretical DFT calculations to understand the reason that graphene oxide support behaves better as compared to graphene acid for the same. So we have a model here where we have the graphene sheet or graphene oxide sheet here with a defect about 4 angstrom, and this contains OH groups and the epoxy group. And on the other hand, we have a model for the graphene acid where we have the same vacancy or defect, but also carboxylic groups instead of OH groups. The catalyst in this case was palladium clusters, 13 atoms clusters acting as the catalyst, and we actually calculated the energy barriers for all the steps of the cross-coupling cycles, and they are closed, the barriers are closed. The first step is oxidative addition. The barrier for this, and this is the barrier for the oxidative addition, is actually the one that determines the overall reaction activity, the reaction rate. So the barrier was, for graphene oxide, was 0.09 EV, and then we have the second step transmetallation. The barrier is a little higher, and then the barrier for the reductive elimination was lower. That's a typical trend in terms of energy barriers for palladium-supported catalysts on actually any support that involves the cross-coupling reaction here. We see a difference because the barrier here, as I said, on graphene oxide is lower compared to graphene acid, although it's not much difference, but it still can see difference, and also the difference in the experimental rate was actually not very much big as expected also from the theoretical modeling here. So for this part, we can conclude this work just appeared last year in applied catalysis, that first, the bimetallic is more active. The bimetallic palladium copper is more active than the palladium catalyst alone. And this is, in both cases, whatever is supported on graphene oxide or on graphene acid. In both cases, the bimetallic is more active. And both the palladium and the palladium copper catalyst have higher activities when they are supported on graphene oxide than on graphene acid, although the difference, again, is not significantly large, but there is always a trend of graphene oxide support provides a better support than the graphene acid in this case. Moving on, so this was the work that's done on carbon-based or graphene-based materials. We turned now our attention to different types of support, which of course very familiar to most of the people here, which is MUFs and bimetallic MUFs. So we looked at different systems, palladium supported on copper BTC, and palladium supported on nickel BTC, and also palladium supported on copper nickel BTC. This is the bimetallic, not the catalyst. This is the MUF support. And palladium also supported on copper cobalt BTC. We did not expect this system. Before I show the results, I just go through the characterization quickly. So this is palladium particles, again, supported on the different MUFs. This is the MUFs itself. This is the copper nickel MUF, and this is palladium on copper nickel. Here is palladium on copper. This is copper nickel, and this one is copper cobalt, is the bottom one here. Palladium supported on copper cobalt. Surface area has the largest surface area on the copper BTC and cobalt. Cobalt has higher, actually a little bit higher than the copper, but the nickel has very small surface area, and all the bimetallics, they have lower surface area than the monometallic, the copper and cobalt here. Turning to the activities, before we look at the activity, I want to show something important here, that the diffraction, X-ray diffraction of the BTC, of the MUFs, this is the MUFs as synthesized, the support as synthesized here on the left, and then we use laser irradiation in solution to reduce the metal ions in water, actually, and with the MUFs present. So we see definitely changes in the crystal structures of the MUFs, which indicates or suggests that opening of the MUF spores or creating structural defects in, through the laser irradiation of the MUFs in presence of the palladium ions, which reduces the palladium ions. However, if we look at, this is another important point I should mention, that the activity of in cross-coupling palladium catalyst always correlates with the percentage of palladium 0. So you need the catalyst to have the highest amount of palladium 0 as opposed to palladium 2+. You can look at XPS analysis of the palladium 3D here, and you can see that in all the palladium catalysts supported on the MUFs and bimetallic MUFs, the percentage of palladium 0 is not that high. It actually ranges between 53 to 68%. A typical, very active catalyst, usually the palladium 0 percentage is 90% and more. So we notice that there is a difference here in the percentage of palladium 0, so we do not expect the activity to be that high because of that reason here. This is just a Raman spectra showing the structure of the support materials, which is consistent with the prepared substance. If we look at the activities now, this was, again, quite surprising results. We know, or we expected these systems, because of the small amount of palladium 0, not to be that active, and we find that these systems are extremely active. You can see the highest one here is palladium supported on copper nickel. Next is palladium supported on copper cobalt. And then third is palladium supported on copper BTC. And the two other MUFs, the nickel and cobalt, are totally unreactive when palladium is supported on this. The activity is very, very high because you can see this reaction time goes to less than 5 minutes, in 2 minutes. Not just that. This is 2 minutes reaction. We have 100% conversion. And the concentration we're using, typically we use standard concentration for the catalyst in palladium cross-coupling is 0.3 mol%. We're using 0.03 mol%. And we're getting 100% conversion in 2 minutes. So what's going on? It turns out that this catalyst actually cannot be recyclable as good as any other catalyst. And it turns out that this catalyst definitely has significant contributions from homogeneous catalysis. So it's not a truly heterogeneous catalyst because of the lack of recyclability of the catalyst. You can separate the catalyst and run it over again. And also, that's suggested by the low palladium content, which was evident from the XPS analysis. So this system actually turns to be mixed between palladium ions activating the reaction and the palladium nanoparticles together activating the reaction. So that's why the activity is very high, because of the first run always involves the homogeneous catalyst systems. So that's not a true expression for what we'd like to develop as a heterogeneous catalyst that can be sustainable and can be recycled over many times. My last approach is to handle this problem of MUFs. MUFs shows very high activity, but the activity is attributed to contributions from homogeneous catalysis. We have another case here, which is one of the famous MUFs, UIO, zirconium MUF, UIO 66. And this is a MUF that we used to incorporate palladium catalyst. And we immediately see that when we do this by laser reduction, also on the MUFs, we produce very small particles of palladium, 1.5 to 2 nanometer particles. This is the MUFs itself, and this is very tiny palladium particles. But if we will go now, so the problem, before I show you the result, the problem is that this is definitely a homogeneous catalyst that involves palladium ions. It does not involve high concentration of palladium zero, which is essential for the. So what we do for this case, we have a process which we actually use to convert the homogeneous catalyst to heterogeneous catalyst. So we take the support, which is a MUF. I'm going to do this quickly because of the time. And we use laser vaporization, which is in inert atmosphere, to vaporize the MUF, to convert it actually to oxide. So we start with zirconium MUF, we convert it to zirconium oxide, but of course there is carbon there, so there is also deposition of carbon materials. And if we use the amine MUF, which is the NH2 MUFs, we contain nitrogen in addition to the carbon. So we end up with oxide instead of the MUF support, and that's what we use to support the palladium nanoparticles. The process we developed many years ago, and we applied it also for MUFs before. This was for MEL 125 to convert the MUF into carbonaceous oxide support for the same palladium catalyst reactions. This is the XRD. I don't, just because of the time, the point is we start with the MUFs, and after laser vaporization, controlled condensation process, we convert it to zirconium oxide that contains carbonaceous materials, or also contains carbon and nitrogen if we start with a MUF that incorporating NH2 groups. This is just the palladium particle size distribution before, which you saw before. This is on the MUFs itself, and this is after the carbonaceous process, after the laser vaporization process. So we have here oxide and carbon, and here we have oxide, carbon, and nitrogen. Palladium is supported on these materials here. Then we go and look at the activity, and we see, as I mentioned, if you start with the MUF by itself, which is here, this is the amine MUF, palladium on UIO 66 amine. Again, the reaction is complete within 2 minutes, 100% conversion. But it's a homogeneous system. It's not recyclable. You cannot separate this, and you cannot repeat this experiment. It involves ions, mostly ions. But if we take this MUF, we convert it to oxide, which you can see the blue curve here. The red curve actually is the one that's palladium on the zirconium oxide after the laser vaporization, and that's also include carbon nitrogen. Activity is lower because this is a heterogeneous catalyst now. We try to add graphene oxide to this support to increase the carbon support amount in the oxides, and we see enhanced activity when we add the graphene oxide. This is with 1% graphene oxide. That's the system that was supported on the amine UIO 66. If we go to the UIO 66 without the amine, same thing, very active as a MUF catalyst, but it's as a MUF support, but this is homogeneous system. But after laser vaporization, we converted to oxide, zirconium oxide with carbon, and we can see less activity, but still not very much less activity. But the advantage of doing this is we can now recycle this catalyst, and you can see here all of the catalysts that's formed after laser vaporization can be recycled, although the activity, as you can see, are lower than the homogeneous MUF systems, but they can be recyclable over several times, and the activity is clearly reduced. So I'm going to conclude here by saying that this is a method to convert actually a homogeneous catalyst to heterogeneous catalyst system through conversion of MUF system like that into oxide containing carbon and nitrogen species. And we can see that using this approach, the palladium catalyst supported on carbonaceous oxides generated by LVCC method provide highly active and recyclable heterogeneous catalysts for cross-cross coupling. I think I'm going to end by thanking my students and the funding agents, and thank you for your attention.
Significant difference in the efficiency. And I don't know really what is the role of copper. And if you compare it, for example, with the MOF, which is the last example, there is no copper. I see still, of course, it's very efficient, but not as when you have copper involved directly or indirectly. Thank you so much. Yes,
we believe that the copper palladium, and we actually studied this system before on oxide support. And the copper palladium, if it's in the form of bimetallic catalyst, they have very high activity, and you're asking about the reason or why above the palladium, because it appears that it enhances the electron transfer process because it helps reduction of palladium 2+ to palladium 0. And the copper is unique in this feature. Yes, play real catalytic activity is an active center. And but it's also without the palladium, it's still active. And that's, of course, a different reason for the activity. But with the palladium, the main process is converting the palladium 2+ to palladium 0.
One more.
Yes.
Nice talk, Samy. So the copper nickel BTC MOF, I see the structure, there's like copper and nickel in ordered states, and I see the ligand is symmetric, so I wonder how the ordered state is obtained.
Which one? Sorry, I didn't.
Copper nickel BTC MOF?
Copper nickel.
BTC?
BTC, yes.
Yeah.
Yes, that's also one of the bimetallic systems that shows high activity. But yes, so what's the structure you're asking?
So copper and nickel, they are in ordered structure. They are occupying different sites in the lattice. Is that correct?
This is in the MUF system.
Yes.
Yes, definitely occupying different lattice, yes.
Yeah. But in terms of coordination, the similar coordination geometry, so I wonder why it can't be in disordered structure.
Because the catalyst is not the copper nickel, it's the palladium that's supported on copper or nickel in different sites. So that's the activities coming from that, not from the copper nickel without the palladium.
Yeah, thank you.
Thank you. Thank you, Samy.
Thank you.